Okay, it's recording now. Good stuff. All right, so let's see what we have today. So we're going to go over, we'll start from matrices, and then we go on to graphs and so on and so forth. Can everyone hear me clearly? Can I be heard so clearly?
Yeah.
Okay. So when I started, writing code, doing some of the interview prep and everything, there's some questions I used to usually avoid, right? I don't know if people haven't experienced that. Like there's some questions, some topics you see there, you see the questions and you just try to avoid them. And for me, questions with matrices was one of those questions. Like I'm at the first, I did one code signal, or it was by Meta. And then the question 3 was actually a matrix question. And I hadn't really done matrices, so looking through it and everything was kind of a hassle. Like I'm not going to spend time on this. So, and it happened to me again on the Goldman Sachs OA. Also, like when I was when I was like a sophomore. And that too was also very brutal because I hadn't really learned to manipulate matrices. And it's like something you should try to do, right? So nested list. It's something you should get comfortable doing. Oh boy. I'm using a new pencil. Okay. Give me a second. The pencil is refusing to. Okay. It's been detected now. Let's hope it's right. Okay. All right. It's good now. Good to go. Okay. So we're going to do two-dimensional. We're just going to do 2D lists. Okay. So 2D lists are basically your standard list, right? So let's say we have one list. Let's call it list 1. And it contains the element 1, 2. And you have list 2. It contains, please follow me carefully. I'm just going to focus on how to iterate through them and how to process them. Then after that, I'm going to show you some questions I think you should solve. That's what I did. I learned how to traverse through them vertically and horizontally, and learned a few properties about them, like their diagonal properties. And I solved a bunch of questions on them. That got me very comfortable with them. So that's a general 2D list manipulation. After that, we'll learn about them in the concept of graphs. Then we also apply it to what you call adjacency list. Let me be good. Okay, so let's assume you have 2 lists, list 1 and list 2, right? If I create another list 3 like this, which contains list 1 and list 2, I get a 2-dimensional list, right? So list 3 is going to look something like this. It is itself a list, then it contains 2 lists, 1, 2, and then 3, 4. So this is what a 2-dimensional list looks like. It's just a list of lists, right? Let's make this cleaner. And so it's just something like this. So what we call a 2-dimensional list, just like this. Now you need to learn how to traverse the elements of the list. So usually I draw it this way to kind of make it easier. Every list is called a row. So this is called a row. This is also called a row. These are called columns. Columns. These are called columns. So if I take this list, it has 2 rows and 2 columns. Point 1. So every single list inside the nested list is actually a row. Every list is inside a row. If you consider the elements across, vertically, we call that a column. So don't confuse yourself. Rows and columns. So if you get if you get a question involving list, you can get the rows by simply saying the length of the matrix. So the length of the matrix is basically your number of rows. I usually call it n rows, right? And the number of columns, n columns, is also, so here we're going to assume that all the nested lists have the same number of elements, right? So this one has, let's change it, pencil. So this one has 2 elements, so 2 elements, right? Like this list, one has 2 elements, one also has 2 elements. That means if I take a column, I can just take one of the elements, one of the list, and use its length as the number of columns. So this is how you get a column, right? So the column is simply the number of elements inside the list, right? So if you didn't see clearly, 1, 2, 3, 4, look at the number of columns we have. We have 1 column here, 2 columns here, right? But you can see that this is the same as the number of elements inside any of the list, right? So the number of rows is length of matrix, right? The number of columns is the length of matrix index 0. In other words, I just chose one of the rows. I just chose like the first row, matrix index 0. I just found how many elements are in to get the number of columns. So that's the first thing to know. This is how you find the rows. This is how you find the columns. Now we're going to look at, going through the list and choosing the elements one after the other. So what we first do, I'm just doing a standard of navigating them. So what I first do, I write for R in range, number of rows. So what I'm trying to do is that, so there are 2 lists here. So there are 2 lists. We have first list as 1, 2, second list as 3, 4, right? So we know this is row 0. This is also row 1. right? So there are 2 rows in all. There are 2 rows in all. So when I do for R in range rows, R, so here, number of rows is what? 2. Let's write the 2 here, right? So that means that R is going to have values 0 and 1. R is going to have values 0 and 1. So when R is 0, I'm actually talking about the first row in here. That is what I'm doing. Does it make sense to everyone? Does this make sense? Does this make sense? So when I say for R in range, number of rows, right, what I'm trying to do is that I know there are 2 rows in my list. So R is going to have values 0 and 1, right? So when I do the matrix index 0, I'm actually trying to, access this whole thing here, this whole row here. Does that make sense to everyone? If you have any questions, you can put in the chat. If I'm going slow, so you can put in the chat. Okay, let's move on. So then I can get the current row by simply doing matrix index R. The matrix index R is just going to refer to, this whole row we have here, right? That is, if R is equal to 0, that's going to be the matrix index 0. And as you can see, matrix index 0, if you look at this thing, matrix index 0 is just list 1. List 1, that is this first list. Okay, now the next thing I'll do is that now I will take a list. So what the iteration does is this. It takes a row. This is the intuition you should keep in your mind. This iteration will take a list. It will take, a list like this, like a row like this. Then it will explore the various elements inside. You know that the various elements inside are actually the columns, right? So this row is actually this whole thing. Now I'm going to enter this whole thing and access the elements one after the other. So to do that, I just say for C in range, the number of columns. Here, we're assuming that they all have the same number of columns, right? So what I do is that I take this as the row, then I take this also, right? For seeing the number of columns. Now you know that the number of columns is actually the same as the length of row, if you look at it carefully, right? It's the same as the length of row. I just wrote this just for writing's sake. So to get the cell, the value in the cell, that value is equal to, you can do row index C to give you the same thing. That is the row is this list, index C, right? So you take this row, index C is going to give you this. Or you can also do value is equal to matrix. You can expand row is equal to matrix index R, then index C. So these 2 lines will do the same thing for you, all right? Let's change this to this. Okay, this is the same as this, right? So this is the row. Row is equal to matrix index R, then do high school math substitution. You can just put it there together. So either of these works. So this is how to get an element inside your grid. This is how to get an element inside the grid. But look at something here. This code we have written here, that's the iteration this way. It takes a row, like it will start from the first row, then to take every element inside the row. So it processes this way. It take the first row, go across it like this. Take the second row, go across it like this. So it processes that row by row, right? But sometimes you get a question where they want you to process it column by column. This is what I mean. So this one is going to give you something like here. So for this code, the output is going to be, it will first take this first row, then to process every element inside it. So you have 1, 2. Then, that is what this inner for loop, that's what it does. It processes the elements inside the row. And when it's done processing the 1, 2, the loop will continue again. Now R will be 1. When R is 1, it will take this second row we have here, this second row here. Then it's also process every element inside it. So then get 3, 4. So this was a row-wise traversal. But sometimes we actually want to have it as 1, 3, right? We actually want to have it as, let's rewrite it. We want to have it as 1, 3, 2, 4. That is, they want to first take this 1 here, then 3, then 2, then 4. That is a vertical traversal. To do that, it's actually not hard, right? So if you look carefully, that's 1, 3, 2, 4. The same as take a column, and process the elements inside the column. So if I take a column, I have something like this. If I take a column, 1, 3 is a column. So see, this matrix actually looks something like this, just like matrices in high school, right? So if I take a column, it's simply this. This is a column, right? This whole thing is a column. So I first take a column, then I'll process the elements inside the column. Those are basically rows. So that for loop is literally the same as this, except all you have to do is to switch the places of these 2. So it's to switch the place of these 2. So you basically the same code, but you switch the places of these 2. That is the only thing that changes. Note, this part does not change. That is a mistake people make. Let me clear this up so to be clear to people. Look, if you want to iterate your grid vertically, right, to achieve an output like this, what you change is this part. Because now you go through the columns first. So your number of columns must come here. So this becomes number of columns. And then for every column, right, you take a column. So it's like for every column, so you first choose a column. Then for every column, you go through the rows in that column. So then this will change to rows 2, right? I usually use C for the column iteration, then I use R for the row iteration. But this remains the same. Value is still going to be accessed as matrix index R index C, right? Now here, instead of row, you can just call it column like this. And this is C. Does that make sense? The row traversal and the column traversal. Does that make sense to everyone? Does that make sense?
Yeah.
Okay, good stuff. Let's go to the next thing, which I think is good to know. Now, if you look at this grid here, right? You know, every item in the grid has two numbers that identify its position. So this is row 0, column 0. This is row 0, column 1. This is row 0. Oh, let me write it by it to the side. Actually, let's do the high school grade stuff. Instead of writing it separate to the sides, let's just write it to the here. Like this is row 0, this is row 1. This is 0, this is 1, right? So the index of, you know, the numbers can easily be computed, right? The index of this is 0, 0. This is 0, 1, right? We say the row first. That's why I said this thing does not change. Whenever you're accessing it, the first thing that should come is a row. Please don't forget. Whether you're iterating diagonal, vertical, whatever, if you write the name of the matrix, its row, the row number of the element should come first, followed by the column number. That is how, because how it works is you first choose a row, the row gives you a whole list, then you index an item in the list, right? That's how it works. Okay, so look at something carefully here. If you look at elements in the, if you look at the elements in the diagonal, right? Let's choose a diagonal. Let's choose this diagonal. Look at the next property. If you choose this diagonal, you realize that the row number plus the column number is the same across the diagonal. This is a very important property to know. Across is the same across diagonal for matrices. If you look at this carefully, so if this is one diagonal, right? This is for 2, it is row 0, column 1. We can see it's right. This is 2. This is 2. It is row 0, right? Row 0, column 1. So 0 plus 1 is 1, right? Is 1. Now, if I take this one, 3 and 2 are on the same diagonal. That is row 1, column 0. So 1 plus 0 is also 1. So for if you take any matrix, right, any grid like this, every element across the diagonal, right, you get it as the sum of the row number and the column number is the same across all. Let me get a question. They want you to just say, get all the elements across the diagonal. It is very simple. It's super simple. You know that all elements of the diagonal are going to have the same position. So all you need to do is maybe create a hash map. You can create a hash map, and they're the same and also unique. It's also unique. Let me show you what I mean by it's unique. Let's assume you have a grid like this. You have 1, 2, 3, 4, 5, 6, 7, 8. Consider the elements across a diagonal. So this is one diagonal, right? This is one diagonal. This is another diagonal. This is another diagonal. This is another diagonal. And this is another diagonal. So if I have 0, 1, 2, 3, and these are the indices of the rows in the columns, 0, 1. Now, we know that for the first diagonal, if I take the first diagonal, right, the sum of the rows in the columns is actually 0. So it would be like for the sum, so let's write sum here, and let's write let's say the cell. Let's call it cell. A cell is basically the number there, right? So here, only this first diagonal has the row plus the column, the sum of the row plus column to be 0, right? So it'll be like, okay, this one contains, is the element 1 that does this. If I take this second diagonal, right, the sum of the row and the column, right, sum of the row here and the column for this guy is also 1, right? If you can see it here, if I take 3, the row is 1, the column is 0, right? So the sum is 1. So I'll take 1 here, I'll put 1 here. Now, if I take 2, 2, if we take 2, 2 is a similar thing. 2, the row is 0, the column is 1. So that one, 2 is, the sum is also 1. So that means that 3 and 2 are in the same diagonal. If I come to the next number, if I come to this 5, it is, row is 2, column is 0. So 2 plus 0 is 2, right? So I write 2 here. So you can see it's actually unique. 2, and then if I take 4, also 4, the row is 1, the column is 1. 1 plus 1 is 2. So you can see that both 5 and 4 have the same thing. So this is literally the code to find all elements across the diagonal of a matrix. All you need to do is simply compute the sum of the row and column numbers, and the elements across the diagonal will always have the same thing. You can accumulate it like so. So that's how you do it. Does this make sense? Does this make sense to everyone?
Yeah.
So enlightening. There's a bunch of questions to come across, and it just works that way. Okay. So we've done one. I need you to be very comfortable with traversing, what do you call it? A 2D list, and also, this cool property about them. I want us to jump to graphs right now. I'll give you questions for matrices to solve this year. Please sit down. Matrices, sit down, solve them. Get your brain used to them. I know it looks scary at times, but don't really be scared, right? Try to solve it and you'll be fine. Okay, shall we proceed to graphs? Or people need a break, a short break? Shall we proceed? Okay, let's give a 30 seconds break. 30 seconds break.
Hello, Cornelius.
Yeah.
Can you go over the diagonal implementation?
Yeah. So this is a diagonal. So should we write the code? Should we just write the code? Okay. So we're going to write diagonal implementation, right? And look at this traversal we wrote here. We're basically going to use the same thing, right? So this traversal was like, so let's say, let's write the code here. So it's going to be like def. Let's use a different color. Let's use green. Okay. So it's going to be like def. Okay, let's call it accumulate diagonals. Accumulate diagonals. Right? Then it takes a matrix. Are we all following? We take a matrix, right? And then what we do is the first number of rows. See, there's this thing about programming. Like sometimes it's good to have a way of writing code, right? So like if I get a question, matrix question like this, I'm not going to think because I have a pattern of writing code. I get my number of rows, I get my number of columns, and then move on. It's not if you're too like kind of open, to anything, like if you don't restrict yourself in some things, you're going to spend some seconds thinking about what should I call a variable? What should I do at this point, right? So sometimes some questions, some patterns, just have your own pattern in mind. Like some of the questions, if people have noticed, I'm just solving them. It's kind of like when I say it's like the same approach, the same pattern, because I don't want to waste time on a question, right? So like sometimes just devise your own pattern. Like me, I just write n rows is equal to length of matrix. I'm not going to think, what should I call this variable? What should I use? No. N columns, length of matrix, index 0, right? This is like 5 seconds saved. Then I'm going to consider every row for R in range rows. There's a variable I missed, but don't want to bring it back. Then for every row, I'm going to take every column inside it. That is every entry inside it. For C in range and columns. Then what I'm going to compute the index, right? Now that I'm going to compute, let's say, the diagonal sum. Let's call diagonal sum. The diagonal sum. And it is R plus C. That is the row, the index of the row plus the index of the column. And that's what we did here, right? The RC was the index of the row, your row position, and the column position. And row position is R, column position is C. So I just compute that diagonal sum, right? And then I'm going to use it now. I'm going to put it inside my dictionary. Let's call it results. Let's put results here. Let's make it default dict. Collections.default dict. We're going to put a list inside. If you don't know this, please watch our initial videos when we did dictionaries. Going collections or default dict. Then I can simply do my result index diagonal sum dot append the element here. That is matrix index R index C. And that is all. That is literally all you have to do. That's like, and then you can return results. And that is all. This is basically how to solve a diagonal question. That is all. Does that make sense? Because we know that all elements in the diagonal are going to have the same diagonal sum, right? All elements in the diagonal are going to have the same diagonal sum. So by doing this, I know it should work. Does that make sense?
Yeah, I think the confusing part was the diagonal sum, like what you wrote in red. It was a bit confusing. But I get it now.
Yeah. So the diagonal sum here means the sum of the row number, its row position, right? Like its row index and its column index, right? So
okay.
That's a row index, that's a column index. Okay. Are we good to go to graphs? And I usually tell people graphs is like I usually tell people like graphs is kind of mini graphs are kind of the easiest questions you come across. I tell people are like so scared of graphs. I used to be scared of graphs too. So I learned it. I'm like, graphs are so flexible, to be honest, because we've done trees and okay, let's move on. So let's go to the graph data structure, and it's really cool. So let's look at graphs. Please, even if you just came, just follow us. We're almost there. Graphs. Okay. So for graphs, graphs are basically a data structure that is used to establish relationship between entities. So, and one company that really uses graphs is like Meta, Facebook, because it's a social media platform. And so they have like, let's say they have like you, and they have relationships across different things. Now, Meta is such an amazing company that the relationships they have is not even just human beings to human beings. Sometimes it's like human beings to other media accounts. So, for instance, this could be like to friends, this could be like the friends relationship, right? This could be like other accounts. So, for instance, if you're on Facebook, you probably have Threads, probably have Instagram, right? Like the entity relationship can be so extensive, right? This could be like the places you go to, right? The places you go to. This could be like your hobbies, your hobbies, right? So graphs actually are so good at showing relationship. Now, even if I take just the one to the friends entity, we can narrow it down like this. So like this one have friends, so A has friends with B, and B have friends with C, right? And then A have friends with E, right? Like this. So if you go on LinkedIn, anything, and if you're A and you go online and look at C's profile, they can tell you have a mutual friend B. How did they know that? Because they can simply traverse this graph and they'll see B, and they can also traverse your graph, your friends, and then also see B. They're like, okay, this is a mutual friend. That's basically what graphs do. They establish relationship between entities, right? In the real world, entities can be your user accounts with your friends, can be you and your hobbies, you and other social media accounts, you the places you go to, and so on and so forth. So graphs are super, super powerful. They're amazingly powerful. Right? Graphs are very powerful. Now, if you saw in trees, we learned about how to go through tree, how to traverse a tree structure. And the trees was relatively simple, right? Because for trees, we also focus on binary trees. So because if you take a binary tree, that's just a left child and a right child, right? So for tree traversal, it was very, very easy peasy. Or if this is the node we are at, we can simply do node.left, right? And get this guy. We can also do node.right and also get this guy. But graphs are different, right? So this is how a tree is. But for graphs are absolutely different. Graphs, there's no limit on the number of children it can have, right? We don't even use children, right? So you can say parents and children. Graphs, we don't, right? Graph, everybody is like a neighbor to everyone. So for graphs, you can have one node. Let's actually use the same thing. You can have a node and it can have its neighbors, a node and its neighbors, right? So a classic definition for a node in a graph, let's try to say class node, a node in a graph, it's we have a definite blah, blah, blah. But the graph node has a value, right? And also has neighbors. And this neighbors is usually a list, right? A list here, right? So a graph node has a value, the value we care about. So here like E, A, B, C, right? And then it has a list of neighbors. Now, how can we represent graphs? There are two main ways we represent graphs. One is the adjacency matrix. The adjacency matrix. Adjacency. I don't like spelling that way, so I'll just make it ADJ. This is how the adjacency matrix looks like. Let's assume you have three people. Let's call them people A, people B, and people C, right? I want to see if they have any relationship together. With an adjacency matrix, I can do something like this. I can do something like this. With adjacency matrix, this grid isn't the best. Sorry. I want to place a cooler grid because people are cool. Okay. A, B, C. 1, 2, 3, 4. Okay. And we have A, B, C again. Ugh. Okay, so for an adjacency matrix, this is what we do. We ask, do A and B have a relationship? So do A and B have a relationship? If they have, we just write 1 here. Do A and B, we are first doing A and A. Every node has a relationship with itself, right? So A and A have a relationship, A and B have a relationship, C and C have a relationship, right? Yes. Do A and B have a relationship? We're like, yes. Do A and C have a relationship? No. If A and B have a relationship, right, I'll actually explain the types of relationship. We have unidirectional and bidirectional. But for now, let's assume if you're my friend, I'm also your friend, right? Let's not think about the Gen Z version of friendship where it can be one way. Okay, so if A and B have a relationship, like here, A and B have a relationship here, that means that B and A have a relationship, right? So we're going to make it symmetric, right? And then here it's the same thing. If A and C, let's say B and C have a relationship. C and A do not have a relationship, but B and this is C and B, those have a relationship. So this is our graph structure. Let's say we can translate this to an actual graph. This is what we call an adjacency matrix. So if you look at this carefully, we said A and A have a relationship. That makes sense. But let's look at A. So let's draw 3 nodes. A, B, and then C, right? A, B, and C. So this graph looks something like this. A and B have a relationship, so A to itself, right? So, sorry, A and B have a relationship. So we can draw a line from A to B. Like so, A to B have a relationship. Then we know B and C also have a relationship because of this. B and C have a relationship. So from B to C, they also have a relationship. Then we know, what about A and C? A and C do not have a relationship. So then this is our graph. We're done with this graph. So this is a construction of this graph. We just represented in a matrix form. That is basically how it works, right? So this is the graph we have translated to this. Now, this relationship we just constructed is bidirectional. In other words, it goes in both directions, but it can actually be unidirectional. Any directional graph. So with bidirectional, realize that it's actually very symmetric. If I'm your friend, you're also my friend, right? But let's assume like a parent-child relationship, right? Parent-child relationship. So we can let a relationship, that is this arrow, represent is a child of, right? It's a child of. So let's even make it is a parent of. I think we can actually make it, or give birth to, give birth to. Or let's say call parents, as in the verb, parents. So if I draw a relationship like this, A, B, C, right? That means that A is a parent to B, A is parent to B, and C, right? So the relationship just goes one way. So these are the two types of relationship. Can be both ways, bidirectional or unidirectional. Now, this is one way of representing matrices, and this is how the adjacent matrix is. You come across adjacent matrix when you solve questions as number of islands and all those things, right? These are questions you actually come across. But note, if you get as a matrix this way, there's nothing scary. There's absolutely nothing scary about them. Even number of islands, that's why adjacency list. Let's look at that. The next representation we look at is the adjacency list. Adjacency list. That is really cool too. That's usually the one I use and the one you'll be using most often. And there are different implementations of it. We're going to use the implementation using a dictionary, which I think is very cool. We're going to use the dictionary implementation. How that works is this. So looking at this graph here, we can see that A has a relationship to only B, right? So we have a dictionary like this. So this is our dictionary. And then let's draw this as a big dictionary. And A has a relationship to only B. So the key is the value of the node, right? And the value is actually a list of its neighbors. So this is actually the neighbors. And it's actually like the node value, right? We called it value. So let's just call the value here, value. So A has a relationship only to B. Now B has a relationship to, as you can see, B has a relationship to both A. As you can see, B has a relationship to both A and C. So for the neighbor list of B, we have A and C. Then C has a relationship to only A. And realize this is like very simple and very, C has a relationship to only B. And this is very easy to interpret, right? So this is very, very easy to interpret. So look at this. So this is how the matrix represented, and this is how the adjacency list will present it. Let's use a dictionary. To be honest, it's so easy to implement adjacency list. You use it almost always, right? There are limitations with the adjacency matrix one. Usually when you use the adjacency matrix one, we usually use positions, indices, because it's using a two-dimensional list, right? The two-dimensional list, sometimes you can't really attach meaning to it because it's feasting off the powers of indexes, right? But if I use adjacency list, I can use like actual things, like the keys, the node values can be anything, right? It can have meaning. So we're going to focus much of our time on the adjacency list. So let's have an adjacency list. So we know it is this graph here. We know it is this graph that we have translated into this. Now let's assume you're given a question like this, and that's what you find all the neighbors. So assume they ask you to find all the friends of B, all the friends of B. How are you going to solve a question like this, right? All the friends of B. Well, it can be like, if I have this graph, I can just do, if I have, let's say you have a dictionary. Let's say you have a dictionary called dict. You can just do dict of B to get, all the neighbors. Wait, there's a question in the chat. Let me take a look. For the adjacency, does it mean for the code implementation, you will have to use a dictionary or a hash mark to find the relationship? Yes, you have to use a dictionary. You have to use a dictionary to define the relationship. Where the key is the node and the value is actually the neighbors. That is how that works, right? And it's very easy it's so easy to construct it, to be honest. It's super easy, right? I'll show you one which actually constructs it. So let's actually use a real example. This is a real example. So we all know this formula. So when I did graphs in 2022, I really hadn't got much time to do it, but I had a couple of interviews coming up. So I solved this question, cost schedule. Those of last year and last year, I told you the same thing. Just solve this question well and understand it, and be so good at graphs, at least the fundamentals. So I solved this question, cost schedule. And by God's grace, I interviewed with DoorDash, MongoDB, a couple of companies, and also asking me graph questions. Karat interviews. I just used the logic I learned from cost schedule. And by God's, I passed every single one of them. Because graphs are so repetitive, at least the basic questions. Let's learn how to traverse it and add some extra logic, right? Now let's look at how you traverse it. Let's look at how cost schedule looks like. Cost schedule is like, those of us who are in school, who have been in school, who will be in school. You have a certain course. Let's say Calc 2. And we tell you that Calc 2, to take Calc 2, you need some. So this is a course, right? And this is a prerequisite, right? So Calc 2 needs Calc 1. To take Calc 2, you should have taken Calc 1. Let's say you have taken maybe algebra, right? Basic algebra. Then to take maybe C programming, you should have taken maybe Python programming. Maybe you're taking HTML, CSS. Then maybe to take maybe distributed systems, maybe distributed. You should have taken maybe Calc 2, and also you should have also taken C. So then they come, we ask you a question, right? Then they come, we ask you a question, listen to a question. We are like, what courses, right? Name all the courses. Let's start very, very basic. What are all the courses I need to take distributed systems? A very amazing class, my favorite class, by the way. Take distributed systems, right? So there's a question. So we give you this dependency relationship. Can you see this as a graph? Because it's establishing relationship. This is a relationship of prerequisites, right? Where this is a course, these are the courses you need, these are the prerequisites. And it's a relationship, it's a graph. I can literally translate this to a graph, right? Where I can be like, I can draw a node for every course here. So I can draw a node, like this is the node for, why are we using too much for it? So this is a node for Calc 2. This is a node for Calc 1. This is a node for algebra. This is a node for C. This is a node for Python. This is a node for HTML. Graphs can be very scary. This is a node for distributed, right? This is a node for distributed. This is a node for Calc 2. This is a node for Calc 1. This is a node for C. This is a node for Python. This is a node for HTML. What is left? This is a node for algebra. So this graph looks like this, right? We have a graph like Calc 2, right? To take Calc 2, you should have taken Calc 1 and algebra, right? So you see, it's a one-way direction. It's a one-way direction, right? To take C, you should have taken Python, and then you should have taken HTML. To take distributed, you should have taken Calc 2, and you should have taken C. So this is literally the graph, right? This is literally the graph. This graph, as you can see, is what we have represented here. Can you see this is actually an adjacency list? This is an adjacency list, right? An adjacency list, and this is actually the graph, right? That scary graph is literally have been reduced to this. So if I want to see all the courses I need to take distributed, can somebody tell me the courses? Can anybody name all the courses I need to take if I can take distributed? Anyone? Can type it in the chat too. What courses do I need to take? What courses do I need to take distributed? I don't take distributed. What courses do I need to take? Anyone?
I don't think you need to take any course or to take distributed.
So distributed has prerequisites, right? Here we say to take distributed, you take Calc 2 and C, right?
Oh, you meant the prerequisites?
Yeah, the prerequisites. Yeah, that's the course I need to take for all of them, right? That means to take distributed, right? I need to take Calc 2 and C. But then you can't just take Calc 2. To take Calc 2, you should have taken Calc 1 and algebra. To take C2, you should have taken Python HTML, right? So you see, it's kind of like you have to kind of like go deep down, and that's traversal, just like trees, right? So if this were like this kind of like a tree structure, even like it's like distributed is at the top. It's like you have distributed at the top here. Then distributed needs Calc 2 and algebra, right? It needs Calc 2, C2, and algebra. Then take C2, you need C1, Calc 1. Sorry, it's not algebra, C. To take Calc 2, you need C1 and algebra, right? To take C, you need Python and HTML. It's something like this, right? Something like this, right? So on and so forth. But we are thinking of graphs. So let's go of this young guy. Okay, so we know, so let's look at the graph structure we have here. Let's look at this graph structure. So we know that to take distributed, right? We need to take Calc 2. We know you can't just take Calc 2. Calc 2 should be like, oh, to take him, you have to go and take Calc 1. Calc 1 doesn't need anything, doesn't depend on anything. So after taking Calc 1, you can just take Calc 1 straight away and come back to Calc 2. Like, can I still take Calc 2? It's like, no, you can't take Calc 2 because you're not taking algebra. Then you go again, and then you process this. Can I take algebra? Yes. Algebra has no prerequisite. Then you come back. Once you have taken these two, once these two are done, you can successfully take Calc 2. Then you come back to distributed. Can I take distributed now? It's like, no, you can't take distributed. Why? Because even though you've taken Calc 2, you have to now go and take C. Then C2 be like, okay, can I take C? No, you have to take HTML first. Take HTML. Can I take C now? No, you have to go take Python. So that's literally how graphs work. Graphs just, you just traverse it, go through the relationship and so on and so forth. What I said is a bit scary, but the code, it's so basic. It's so basic, to be honest. Let's see how the code can look like. So as somebody said in the chat, we have to take all the courses. So it can be like def can take course. So let's just call it gets all prerequisites. But let's just say can take course. Can take course. And let's say courses to take. Let's say courses to take first. Courses to take first. Okay. So I give you a certain course I want to take. Down to you tell me all the courses I need to take first before I can take this course. So first of all, I'll check. Look at something. For implementation of a node, right? a course is going to be represented by a node, as you can see in this graph here, right? So first of all, you construct your, I'm going to just give a few things, just go and write the pseudocode kind of, right? Because we don't have time. We have to end soon. So this is a node, right? So we're going to actually construct an adjacency list from it, right? This is a node inside the prerequisite it takes. But look at something here. Our course is actually the string here. Is a string here. And then, this is its neighbors, right? And then we're going to call this graph, let's just call it, what? Map. Let's just call it map, right? So the first thing I'll do is this. I'll first check, look here. If map, let's use uppercase. If map of this course is empty, that means this course has no prerequisites. Do we all agree? Like here. So if I consider the actual map, you see that Python has no prerequisites. So Python is empty, right? HTML has no prerequisites. So HTML is empty, right? Calc 1, same thing for Calc 1 and algebra, right? So if map of course, so this is the base case. If the course has no prerequisites, right, then that means that I can simply return the empty list, right? In other words, there are no courses to take before I take this course here. But if it is not empty, then I have to go through each of its courses, right? For each, let's call it for every prerequisite, let's call it prereq in map of course, right? So I go through here, then look at it. This thing we're talking about, recursion. Assume the function works. So for every prerequisite, all I have to do is to get the courses to take that prerequisite, courses to take prerequisite of that prereq, because the prereq is also a class. Then after I get this, let's call this temp. So I get all the prerequisites I need for that course. Let's say the result is the variable we are going to return. Result is called to the empty list. So when I get a prerequisite, when I get the courses to take for this current prerequisite, I just add it to my result. So result plus equals this temp. Temp is not the best name, right? And then, are we following? Is this making sense? So
Yeah.
if I want to get the course I want to take for distributed, I first get all the course I need to take for Calc 2. So I'm believing the function works. So now this function is going to return to me Calc 1 and algebra. So here temp is going to return Calc 1 and algebra for Calc 2. Does it make sense? So then I add Calc 1 and algebra to my result set. But that is not all. I also need to add Calc 2 itself. Res.append Calc 2. I mean prerequisite, not necessarily Calc 2. And after that, I just return rex. And this is basically the whole solution. This is literally the solution. Like we are done. This is the whole solution to solve this question, right? And it's recursion, right? And it's so intuitive. But if you get this question in the graph, you probably get scared. But there's nothing scary about this. It's the same template we have been using. It's the same template. The only thing we changed, it's also similar to tree traversal. If a tree traversal, instead of a for loop, we'd have just used call the function or node.left, call the function node.right. But here we don't really have a notion of node.left, node.right. Instead, we have like a neighbors set, which we are calling map index course. Map index course is going to give you, the neighbor list, right? Does that make sense? Does that make sense? And this is the whole question. This is the whole solution, to be honest. That's the whole solution. Are we good? We good? Yeah, we good. Okay. So this solution we actually did.
Wait, please.
People don't have to.
Okay. So my assumption is that was it me, or like you didn't run courses to take on? You see, you are writing a recursive function. So when you get for each prerequisite in the for a certain course, I assumed you are going to run the recursive call on those prerequisites.
Yeah, that's what we did here.
Like, oh yeah, and then you appended it to okay.
Yeah.
Yeah, I missed that part.
Yeah. So we just assume the function works, right? So like if we call the function on the prerequisite to give us the prerequisites of that prerequisite, right? So like we are undistributed. Then Calc 2 is a prerequisite. Then we call the function on Calc 2 too. We are believing the function works. So the function will bring us Calc 1 and algebra, right? And then we get this. If you have not watched our recursion session, please watch it. To make this code make a lot of sense to you. But you see, if the code needs, if you just write this, you don't have to explain the recursion, to be honest. You can just sketch this and just be like, we go here, then this will go here, add everything together, bring it here, power, and you're there. That's it. So that's basically the implementation and the very cool stuff. So graphs answer the scariest thing. Now, this approach is actually what we call DFS, depth first search. How is it DFS? It's DFS because if you look at the code, we take the prerequisites of distributed. Then we take the first one. Then we try to get the courses to take for that first one. That first one too is a list, right? So like here, we are like distributed. We take its first prerequisite, Calc 2. Then we call the function on Calc 2. Calc 2 will come, Calc 2 will take its first prerequisites, Calc 1. Then to call the function again. So like it goes straight, it goes deep first. After it's done, then to come back, then to go deep again. That is what we call DFS. DFS does deep stuff, right? It first go deep. And that's why, and you can see the recursion here, it just goes deep here. To make it even clearer, let me show you this. So we have distributed here. Then we have calc 2. Then we have C. Then we have calc 1. Then we have algebra. Then we have C. Then we have HTML. Then we have C. What was the other one? Python. Right. So this does something like this. If first it's a distributed, like let me check this prerequisite first. That's calc 2. Calc 2 is like get my prerequisite first. You come down to calc 1. So after you see calc 1, the base case will catch calc 1. But calc 1 doesn't have any prerequisites, so to just return. Oh shoot. I mean, this is fine. I mean, we could have actually appended this to this. You could have done, see this part, you could have actually done it here, but you can also do here to work either way. So you bring calc 1 here, then to go here. So that's DFS. We can also do BFS. BFS is different. BFS, we looked at the code for BFS 2 weeks ago, the template for writing BFS. BFS, when it starts here, it will explore calc 2 and C, like, you know, in a certain way. And then it will come here to explore it, to do it level. But that's something you should look at if you've not watched the video from previous sessions. And yeah, so that's basically, that is literally it. So this is a good intro to graphs. I hope you really keep the stuff in mind, and let's talk about the materials for God willing this week. So to be honest, almost every graph question you come across, this is basically the template. Once you understand it, right, the traversal should be easy peasy for you. Learn how to create your dictionary, right? Learn how to create this guy here. It's so important. Learn how to create this guy, learn how to traverse the guy. That is all you need to know. There are questions there that you'll be solving this week, like number of islands and those things. To be honest, you can easily do it. There's also other things. So for instance, let's assume, let me just add the other spice. Let's assume now, I told you that, look here. Let's assume that now we told you that to take algebra, let's assume I told you that to take algebra, follow me carefully, take algebra, you need to take calc 2. So I'm like, to take algebra, so let's add that dependency here. I'm like, to take algebra, you need to take calc 2. You take algebra, let's assume you take algebra, you need to take distributed. Let's say you take algebra, you need to take distributed. So as you can see, that means that to take algebra, you can see this algebra, you need to take distributed here. That means that there's no way you can ever take distributed because it's a cycle. Can you see there's a cycle? A cycle because, look, you come to school, you're like, oh, to take distributed, take calc 2. Take calc 2, take algebra. To take algebra, take distributed. It doesn't make sense. That means it's a cycle in a graph. So it means that you cannot take distributed. There's a question like that. Can you take this course? You simply want to check, is there a cycle in our graph? And there's a very easy way to check it. You just have to traverse it. And if you see something, if you see a course you have seen before, just tell us no. I've seen this course before when I was trying to take it, and I've seen it again, therefore no. Well, next week, we'll talk about memoization. But I still want you to get exposed to it this week. We'll go over it deeper on next week. Even as you do the practice, you come across it and then you'll be fine with it. But yeah, let me show you the materials for this week. We're a bit behind on time. I usually want us to close exactly on 2, latest 2:10, but let's see what we have here. Okay, I hope it makes sense. I hope we didn't get confused for too long. Yeah, my chemistry teacher, ABK, said, if 1 or 2 people understand, he has done his job. Okay, so I think I've done my job. Have I not? Hey, you know, like I've come across many people in meetings. The whole people probably give blue ticks. All the people I've met in this life. Take a people, blue ticks. Okay.
Oh, I just say my voice was lagging.
I see. Okay, so there's no
Yeah.
blue ticks in here. Okay, that's good. You have made my day. Okay, let's see what we have for this week. Screens. Let me share my screen. Can you see my screen? So for this week, can people see my screen? Why is it not loading?
Yeah. Neat code.
Yeah, good stuff. So today, I mean this week, wait, is it down? Wait, his site is down. Oh, wait, can someone try opening at the end? It's like it's
Yeah, I'm checking.
Maybe now I'll just show you the questions on a different platform. But I wanted to use here so that
Yeah, seems like it. Nope,
down, right?
it's not down.
So the data is not there, right?
The data is there for me.
Oh, so it's just mine.
Yeah, probably.
Oh, really? How is that possible? I have no issue with him too. Oh, that's unfortunate. Oh, actually, wait. Um, okay. Let me use his playlist. I have to message the guy. I don't know the issue I have with him. Or the issue he has with me. On the graph problems. Okay, so you can go here, and then what you do is please like learn it. See, I told when you start, just learn it. See, like you can look at the top 5 common graph thing he's saying here, and then look at the first question. Cost schedule is even the first one here. Then you go to lead code. It's literally on lead code, to be honest. So you can open this first video. Then you just, does he have the link attached? No. So you go to lead code and open the question. You try the
Hey everyone,
question.
welcome back. Let's write some more neat code today. So
when I was unemployed, I used to listen to the guy. Okay, and then you just watch this and solve it. Try to solve it first and reason it through using the let's say we have discussed. So based on what we have discussed right now, I would say you should first try to look at, after you try solving yourself, try to look at a solution by someone and see if you can understand the code before you watch neat codes on. Right? Or even neat codes, it usually has the code snippets to the side, right? Oh, it's back. He heard my threats. I was threatening him. Okay, so like course schedule, try to look at the code, like open the code like this and try to look at the code. So you can see here, this is a map. The map we created, the same thing he has created, right? He creates a dictionary, then he populates it for every course and its purposes. Then what he does is that it's the same thing we did, right? If it's empty, right? If you have no prerequisites, that means I can take you. I can just do you straight away, right? If not, I'll go through all your prerequisites. Then I'll see if I can take every one of your prerequisites. Then I'm there. That's all. That's the whole code. And see the funny thing. Most draft questions actually that pattern. See, not like this guy's K. It's the same thing. He just did a BFS here. Look at the DFS approach. It's the same thing, right? Consider all the neighbors. For a grade, the neighbors are north, south, east, and west. This is how you just do that. So we'll do this next week. We even did this last year. North, south, east, and west. Just it's a base case and a for loop to go through the neighbors. Almost most graph questions, that's literally it. There's just a few things like union find algorithm, which we'll look at later. We'll look at all the others, like the same thing. Look, just neighbor. This is also a, what do you call it? A grade 1. So as you can see, you go through the rows, you go through the columns, and then just process them. Like the same thing. So if you learn once and for real, like graphs become like your best data structure, to be honest. I learned just course schedule and I was fine. But you have to learn more. Because the following year I learned more. So like the same thing, the DFS, visit, the same thing, the same thing. So on this week, we are killing this. I want you to sit down and master graphs, to be honest. Like companies love graphs. All the questions here, all the medium ones. Once you're done with the graphs, go here, go to leak code, and go to the problems. And then go to matrices. Actually, I want you to also solve like some 10 matrix questions or some 5. You see some of them as you do the, but I want you to still, I want to find some matrices. Isn't like no matrix. Oh, here, matrix questions. And let's try to do the easy ones to get familiar with iterating through a matrix and those kind of cool stuff, right? And then you get comfortable with them. See, I've done a good chunk, as you can see here. Yeah, I'll share the column regression. Sure, I will. Yeah, well, our regression session is just magic. You just need to assume something and it works. So yeah, so just go through these ones. I went through a good number of matrices because I wanted to be comfortable with them. So do some matrix questions. Some are just do the easiest and just to get comfortable with manipulating matrices. Then you do the graph questions. So please, we're doing graphical on this week. I'll share some resources, but to be honest, the session we've had right now is literally enough. See, there's a reason like we have these sessions. They're literally enough to start solving the questions. But after you solve the questions, you learn more things, right? Okay, we're done for today. Any questions? I'll share this recording too. And then, yeah. Any questions? Any concerns? Anyone wants to give me money for today? Obviously not. Okay. Okay, I will catch you folks, God willing, next week. If I've not replied to your message, ping me again, I reply. See, I reply, but just can't be sometimes. But yeah, please go through the resources. grind hard, practice. I know some of you have always in interviews, don't worry. Still practice, right? Like, you'll be fine. You'll be just fine. Just practice hard. Some of you, speak with us, you're like, oh, you are picking up. I did this, it's worked. I'm like, yeah, see, that's the thing. The more you practice over time, code you write, you get more confident, you get more comfortable with the material. So please, don't slack. Just practice like consistently. Your brain picks up. You're going to write recursive code so naturally, right? Some of you think we were born with problem-solving skills. No, it comes with practice, right? Like, I didn't even go through any graph materials before today's session, but by God's grace, I practiced like months ago, and very consistently. So please practice and make money, yeah, and go build Ghana for us and Nigeria and wherever you want to build. Okay, thank you. Bye. And nobody even said bye back. How are you people?
Bye.
Bye.
Don't worry, I've not forgiven you. Okay.